So hi guys, as introduced, the topic for today will be gotta go fast. So a bag of tricks, speed up models and parents in production. So MOPS edition, just generated. Okay, so before we start, quick introduction, but really quick one, as probably you guys are, eager to get a pizza. So as mentioned, my name is Michał Mikołajczak. I have a machine learning data science background. But this is background, and as I worked in the field, my role kind of evolved because I was involved in quite a lot of startups, medical ones, and we had really cool models, but we came to a point that, hey, what now with them, right? We actually need to deliver them to the users. Someone had to do it. It was me. And my role kind of evolved, right? So I started to deploy those models, architecting around them and so on and so on. Fast forward, some of the startups developed, started actually deploying those models in production. I became CTO of one. It was later acquired by Nasdaq and so on and so on. Currently, I am an tech lead in DataRabbit, in which we are doing end-to-end machine learning solutions, right? So with, from the modeling to actual deployment. And during this deployment, we also often are handling inference, which will be our today topic. In terms of the agenda, we'll do a quick primer first, right? What's actually is inference? Why do we care about production model usage? What are the benefits of it? Then we'll go to hardware acceleration, how it can be done, what are the trade-offs. Then we'll actually move to model level or software level optimizations. Do a quick stop about why do we need to profile and test all those solutions. And last but not least, Q&A. Okay, so you're probably familiar already with this MLOps loop. Essentially, we are starting with some design, right? So we are gathering all the requirements from business in order to make the actual, use case feature successful. We need to start with that. It is crucial. And later, this is what data science folks and so on care the most, right? And this is also, the cool thing. Right, so quite a lot of data engineering, model development, in order to get all those fancy algorithms, which one is working better, right? Maybe this one is 0.5%, more accurate, right, and so on and so on. We're spending quite a lot of time there, right? And then we have the operations and deployment, really often overlooked. And if we are spending that much time with development, right, of those models, shouldn't we also care to make sure that they are working well once deployed, right? That we are working reliably and fast. And obviously, the answer is, yeah, we should care about that. Some solutions even wouldn't be possible without the fast inference. So any kind of predictive analytics for like stocks, financial markets, and so on. This is something that needs to be sub-milliseconds even response. Another case, cybersecurity, right? So if we have some attacker that is entering a network, we are detecting that with algorithm. We really need to, for everything to happen really fast, right? If this attacker distress is actually in the system, right? It managed to steal the data already, and we are only now getting, model responses, notifications, right? We are not really care, right? Again, self-driving cars. So similar situation. We need this answer immediately in order for this to be useful, right? If I get a notification that, hey, buddy, in the front of us is a tree, right, to run around. If I get it once I hit that tree, not really that useful, right? So the benefits of that are, some of the solutions are just enabled, right? The other ones are scalability. So the faster we can deliver the predictions, simply the more requests we can actually process. Another one, user satisfaction. So we as ML folks, we often, the training is not really, if we have to wait, it's not even that problematic it's not really that problematic for us often, right? So we can, do some development in the middle, write some tests, maybe catch up with some papers. But on the other hand, if you're a user and you need to wait a couple of seconds for the response from the product you are using daily, not really that fun, right? Just imagine that you are, for example, opening a website, and every time you need to wait a couple of seconds for that. So not really a good experience. And if we are actually processing everything faster, then we can reduce the cost of hardware, right, and hardware requirements. If we are actually using smarter methods than just simply extending the compute resources to do that. So in terms of hardware, what we can do to speed things up, employ dedicated hardware accelerators. So GPUs with NVIDIA being dominant here, not really a surprise. Some of those cards are even inference oriented, right? Dedicated only for inference, like AWS Inferentia or NVIDIA T4, TPUs, right, from Google, and all of the sticks, right, for example, or those pluggable accelerators like Google Coral, Intel Videos, stuff like that. But the easiest way, is simply to have the faster inference, is to extend the compute, right? Either by vertical scaling, so improving the machines that we are working with, adding more CPUs, adding more memory to existing instance, maybe the GPU accelerator, or horizontal scaling. As we are adding more resources in horizontal fashion, simply more nodes, and then essentially with that I could scale indefinitely, right? I can add more nodes, the traffic will be distributed across them, and I will get all of the data will be processed really fast. The problem with that is, essentially it also costs money, right? And we are in a situation like that. We as developers, we might not care about that much. We might even overlook that. But at the end of the month, right, well, the management sees the bills, right, then the trouble begins. But the thing is, even with this compute, even with this hardware, you can be smart, right? So better compute does not always account to more costs. And here we'll go through a practical example. One of our previous projects, the context of that is healthcare. Basically a 3D processing predictive pipeline for segmentation. So, a 3D processing pipeline, 3 models in total, rather heavy. On the other hand, it was a limited internal pilot. So we just, the assumption for that was that, hey, we just need to process 10 studies. So basically 10 scans, 10 patients in a day in the system. And, that was it. We had a limited budget, right, for that, $200. And initial approach, just for POC, just to have it, deployed somewhere, right, was just to have a container and running on a single node, single VM. It was constantly up. Here are the node parameters, right? So nothing really that big. The price is something like 50 cents per hour. Average study processing time for this pipeline, as mentioned, it was 3D, it was quite heavy. It took 30 minutes. And if we compute all that, average daily cost, we simply need to multiply 24 hours by the hourly rate of a machine. We have something like $13 per day. Does not fit our assigned budget of this 200, and by quite a lot. But the next version, modified approach, we are using same node, right? So full CPU, but with auto-scaling employed. It doesn't work very nice. Machine is only provisioned, right, with auto-scaling when the processing request is in the queue. So we need additional 5 minutes are required for something to scale up, right, the node, 15 minutes for scale down. And this time is also billable, right? But still, we have the very same parameters, but given the fact that we do not have these machines constantly up, the processing time per study goes to 30 minutes, so the original pipeline, plus 5 minutes for scale up, 15 minutes for scale down. We have this 10 studies average, and the daily cost is reduced like 3 times, simply because we are only spawning the machines when they are needed. This one fitted our assigned budget, there's a trade-off that we need 5 minutes more before the users can see the actual results. But you had this spare budget, further experiments were conducted. So same setting as before, but this time we're actually, going the opposite direction, right? Utilizing more expensive machine with the GPU. So this one have slightly less, like half of the original CPUs, slightly less memory, but it has the accelerator, right? NVIDIA T4. The price is higher, but the average processing study time went down to just 5 minutes. And with that, we compute all of that. 5 minutes for the processing, 5 minutes for scale up. Still, we have this 15 minutes for scale down because autoscaling is still employed. But the cost, even though we are utilizing the machine that is technically slightly more expensive, went down, right? So it not only fits the assigned budget, right? Not only it is cheaper than the version 2, but we have a trade-off. There's still trade-off that we need this autoscaling. We need this 5 minutes for before the users can see the result. But actually, they can get these results in only 10 minutes now. Yeah, and basically here it's visualized, right? So in the first scenario, user needs to wait 30 minutes for results. The second, 35, but it is cheaper. Now, and the third one, not only cheaper, but really faster. So, GPU are actually doing the work, right? And I know that probably for most of you it is already known, but just in case, always try to look for accelerators, basically a no-brainer gain in more complex models. Also, another thing, most of the cloud providers, they have different pricing models. So the basic one is that simply you are paying by the hour or second of the compute time of the instance that you're running on. So we are spanning something like EC2 machine on or Node or VM on Azure, and simply pay by the hour. But you can also save the cost, reserve something for like 1 or 2 years. Theoretically, you can save like 70% on that, simply if you reserve the machine in advance. In practice, it is less, right? Those are the marketing numbers, I would say, but still something worth considering. And the last but not least, spots, right? So you simply are paying for the machines that are not utilizing at all, but in the cloud provider. And there, the prices can go up to like 90% discount. Theoretically, the problem is it can be interrupted, but still quite a lot of solutions that we deployed utilizing that in practice, right? And it's, if you can handle the retries, that's very good alternative. Okay, with that, moving on to software. So, first thing that always you should utilize, always you could look into, batching. So taking advantage of the GPU parallelism. The GPUs are working the best if they are fully utilized, and the most naive approach that we are seeing often with our customers is that they are approaching models that, hey, we have a single sample to process, we are processing single sample at a time, right? Even though with training, it is counterintuitive, right? Because in training, you're also always trying to have the batch size, right? Have it the biggest as possible, right? And then, they are going to production and, doing it piece by piece. Obviously, this is easier to debug, for example, right? Something more predictive, I would say, but not the best way, again, to utilize the GPUs. It introduces unnecessary overhead, and processing the batch is really more efficient, right? Usually, the more we can fit into the batch, the better. On the other hand, the problem, the complexity that it introduces, we needed some batching component in the system. But that's not really a problem. Most of the inference handling framework, like NVIDIA Python, that reference architecture you are seeing here, handle that by us, handle that for us, right? So there is a batching command here. It's simply, as the requests come in, they take care, batch everything, and only then process it through model. All automated. And even if it wasn't, right, you just needed queue, right? So something that you can hand code by yourself pretty easily. Yeah, here is just the numbers for YOLO 5. If somebody does not know this, this is an object detection model. Not that we really care. What is of interest to us is the inference time on the x-axis and on the y-axis, and on the x-axis we have the batch size. And you can see that there is a pattern, right, the logarithmic one, that basically the more we go with batch size, the better benefits we are getting in terms of inference time. You know, it starts to slow down basically, but really impressive compared to what we had originally. And it is all on the same GPU, right? So no change in hardware whatsoever. We are only modifying the parameter, right, for batch size. Make sure that we are fully utilizing this hardware that we have underneath. Of course, the situation gets more complicated in case of LLMs. So I've added this one after the first presentation. Essentially, you know, in the LLMs, the problem is that there's the length of sequence, the length of what you're generating, this is not known, right? So the batching becomes more complicated there, because one sequence can end, you know, at some point, the other can end sooner, right, or maybe later. So basically what you need to algorithm handle to, you know, as it is generated, look up this called continuous batching, and essentially, you know, you're looking for the end tokens, right? And only after you have the end token, you are inputting the new sequence new sequence into the GPU for processing. Still, something that many of the inference tools, inference frameworks are actually handled, right? So LLM serving frameworks like VLLM or TGI, those are things that support those and many more optimizations like page attention or similar stuff out of the box. So their usage, highly recommend. Next thing that we can do software-wise, right, I would say, or model-wise, quantization. So, you know, historically, all of those neural networks weights were stored in 32-bit floating point format. And quantization is simply a set of techniques to represent the weights and activation with lower percent data, such as, you know, FLOP 16, int eighth, or, you know, recently, even smaller. This is a bit dated, right? It is int 4, now we have, you know, like int 2, right, even int 1, and so on and so on, but that's the idea. And, you know, the result from quantization is that you are significantly reducing the required memory, but this is also faster, simply because, you know, floating point 16 is faster than floating point 52. The int arithmetic is even better, right, for the speed of the processing. The problem, well, the trade-off is that precision is also reduced, right? So obviously accuracy might be affected in the process, but, you know, the question is whether that trade-off is acceptable, right? So, for example, we had two cases. In one, you know, some segmentation model, some visual model, we performed, simply started utilizing FP16 instead of the original one, right? And no difference in results, nothing visible whatsoever. On the other hand, playing with LLMs, right, with Mistral, I think, recently, and, you know, as we are going to inf 8, right, it was good, but going lower, it became a drooling neural dummy, right? Essentially, it stopped generating anything useful. So always something that you need to test out, right? Whether this trade-off is acceptable for you or not. And good news, right? For many popular large models, this quantized version are usually available already, right? On, for example, Hugging Face Hub or similar model hubs. So, you know, you can have just a snippet of code, you know, load it in quantized version, and that's all that, ready to use. So obligatory, God bless Hugging Face. Last but not least, well, not really last, inference optimization frameworks, right? So other than these generate methods that we had so far, right? Because batching quantization, this is something that you can universally use. There are also some dedicated platforms or compilers that optimize the models for inference on specific hardware on machines. So, for example, Intel CPUs or NVIDIA GPUs, And they apply a range of optimizations that are specific to this particular hardware. And examples are being, like OpenVINO for Intel compilers, NVIDIA TensorRT, Torch compile, right, on its runtimes and so on. And they are giving quite a lot of speedups, right? So we can see this is those are the results from Intel extension for scikit-learn. And you can see it even goes to like thousands times faster inference than original one. Still something to take with a grain of salt. Given personal experience we had, it usually, those are then marketing numbers, right? Marketing benchmarks. It might be not as good in your case. It wasn't in ours when we were testing all that, but still something worth looking into. Essentially, as many of those tools are really easy to use, as I will show in a moment. And the best one, at least for deep learning, TensorRT, right? So this is a king. This is simply a king that takes the crown in most of the benchmarks for data centers for high-level scaling. And as mentioned, all of those, in the past, it was harder, right? In the sense that you had a complicated instruction and so on. Nowadays, most of them, or many of them, are very easy to use. So this is all you need to do in order to utilize TensorRT, for example. So, you are specifying some minimal shape, right? Maximum shape of what can get into that. What precisions are you interested into? And that's it, right? You're calling TensorRT compile. Oh, the magic is done. You are saving the ready model. You can later, just load it with PyTorch. That's it, ready to use. At the same time, being drastically faster. Now, all of those methods that I've talked about, they're all, I would say, industry standard, right? So utilizing those frameworks for those platform-specific frameworks, batching, right, quantizations, those are things that actually people are, I would say, they're used daily, right, in pretty much every pipeline that we're dealing with or customers are dealing with. Here I will talk about some more experimental ones, right? Maybe not experimental ones. They're really established, right? For example, model-based pruning. So the concept here is really simple, right? You're looking into the weights that have a very low magnitude or very low impact, for specific, for the output of the model, and you prune them simply. So get rid of them. In the ideal world, you have less parameters, it should all work faster. And that's the theory. The intuition is good. The problem is, that many of the software many of the hardware tools does not really support sparse operation. So those are the problem here. Those ways are becoming sparse. Universal tools are still early in the development. Still, there is lack of hardware support for something like that. Hence, I would say adoption is limited here. Another thing, knowledge distillation. So another concept, you have a teacher model, which is something that is very big, and you try to perform knowledge transfer to some smaller model, right? It learns to actually output whatever the teacher model learned initially, and again, all is sound. The problem is that these big models usually are big for a reason, right? So this knowledge transfer is limited in most cases. Still, there are examples that it actually works, right? So, for example, Alpaca from Stanford this last year, right? But it was really hot topic back in the days. It was trained exactly in that way. Again, something that is really universal and, for example, ideal case for, like edge device models. Last question, right, the last stop. Why test if you guess, right, or think that it should work? Simply, to be a good citizen, always try to, you need to always evaluate whatever optimization that you are performing. You need to actually, have those results so that you can get back to them, so that you can actually report them, see if things are improving. Just as in, changing the models in data science, you should maintain the same framework here. Make sure that you have a proper test set. So ideally, it should cover all the edge cases, all the whole distribution of data, and so on. you are doing on the very same hardware equipment that you will be running in production, so in terms of CPUs, amount of RAM, GPUs, and so on. And in general, not only hardware, but Docker images, libraries, and so on. Another tip, collect not only time, but also utilization of all metrics, such as CPU, GPU, memory, split it into different steps, right? To make sure that you have pre-processing, post-processing captured, and inference captured separately, just so that it improves your ability to later actually identify bottlenecks. And run those tests multiple times, to reasonable degree, because it all costs, right, to average the results. And again, all for maintaining the historical results for future comparison, right? You are doing it right now, you have some results, but half a year from now, either your team, right, or you yourself will thank you for that. Okay, so the summary. So faster inference is almost always desirable, right? In some cases, it is necessity to even have the solutions that enabled, right? In other, it translates to better user experience and lower costs, right? If done smart, not that by just throwing the more money, right, more hardware into the problem. Faster inference, it is usually a trade-off with either more operating cost or at the cost of decreased model accuracy. But once again, the key is a trade-off, right? Is it acceptable for you, right? If the model accuracy, for example, decreases by 1%, but the inference is 40 times faster, probably worth it. And again, many of those tools, right, are really easy to use nowadays. So, the example with TensorRT that you saw, it's something that is really really easy to get into. And always run those tests for any optimization deployed in an environment that is mimicking production setup. Maintain the results for the future. All right, so that would be it from me. If there are any questions, I'm happy to answer them. If not today, right, here are two LinkedIn codes. One is for our website, and the top one is for me personally, right? So if you have some, topic questions about the inference, but also other stuff, right? Happy to help however I can. And I really mean it. I will also be, enjoying pizza in a moment, right, with you, so feel free to talk to me.
Thanks you for your presentation. Do you have any questions?
I have a question. Thank you for the presentation, and it was a very comprehensive overview of the techniques. And I'm very curious about your personal project experience with applying the models to with this technique. So could you share a bit more which models you integrated with TensorRT or with the quantization? And were these open source models or custom made or fine-tuned? What kind of architectures were these?
So I would say the usual answer is always it depends. But in general, the practices or the patterns that I would say from the experience, TensorRT, for example, for speed up of deep learning models inference, it is really good. It is no-brainer, always worth to test out. We're testing it out our segmentation models, right, in particular, or in general, vision stuff, and it works really well. In a sense that there might be some performance degradation, but it's definitely worth it if the models are running 3 times faster, right? So that's the first thing. As for quantization, for example, this is something that you won't be able to serve large language models nowadays, right? Because they have the trillion parameters, right? You need to, well, of course, if you are NVIDIA, maybe you can, right? But if you are actually, GPU pure, I would say, nothing you can, you need this quantization in order to even run the model memory-wise, right? So in terms of LMs, quantization is a go-to. It always needs to happen, although maybe not even for the inference speed up purposes, but simply because of memory, right? So as mentioned, it is always a trade-off of multiple dimensions. So that would be like general ones. So I would say whatever is easy to use, right? Try it. In the sense that TensorRT, really a good thing to go, right? Quantization, simply necessary. Other than that, it depends. But often, just making an architectural level decisions. So the first case with hardware that we had presented that maybe you can, do batch processing, and then you can only have the machine for running for a couple of hours, but you can employ a pricier one, right? In that case, so yeah, depends on the scenario, but those are the, I would say, 3 things that I would say.
How would you usually achieve autoscaling to 0 for ML models? So like what platforms, tools?
So again, I repeat myself. It depends. But the thing is, usually queue-based, right? In the sense that you have a bunch of requests to process, and you monitor it for how many items, requests, and so on you have to process. Basically, that would be the answer. It largely depends on the ML system, right? Because the ones that I was giving examples. Those are really, I would say, complex in a sense, always 3D and so on. If you have, for example, something that is serving the really simple predictions, right, some linear regressions, cycling the model and so on, you probably want, in that simple cases, you probably can have them, put into some lambda and so on. The problem, it depends on the traffic, basically, unfortunately. So if you have in many scenarios, simply because you have traffic, you need to serve, the answers in reasonable latency, you won't be able to, scale down to 0, right? But in the more complex cases, like, like these medical ones, or some very small ones, then you can probably try to employ different tools based on either queues or simply serverless.
Yeah, thank you for the presentation. I have a question regarding the trade-off that you mentioned. If it's usually human evaluated, or there's some kind of metrics that you usually implement, or like what is the possible thresholds for the when it's feasible or not to make this trade-off between speed and accuracy?
So the situation here is, usually I would say from my particular experience, is usually you have some constraint, in a sense that, we have some accuracy that whatever accuracy metric, right? I'm not saying just accuracy and so on, but we have some precision metric that we simply can't go below, right? Because those are the business requirements, right? So for this one, might be one constraint. The other that is seen often is budget, right? So simply, you have fixed budget. For example, I don't know, thousands of dollars to run everything monthly, right? Just to have some example, and you are said that do whatever you can, right? But you can't cross that one. So usually it is optimization with some constraints or boundaries in mind, and other than that, simply you are trying to get best of what you have, right? In terms of automation or metrics for that, I wouldn't say. I don't have anything automated myself. It is usually, like human evaluation in a sense that, hey, we can actually spend this and that, right? Compared to this accuracy. You're talking with business, but essentially it is not something that, for example, like retraining models daily. It's simply those kind of optimizations are rather happening on less frequent, right? And it's not really automated, at least not in our case, not in the customer projects that we have.